Okay, we're just about ready for our last tutorial session of the day. Before I do that, I would like to take a moment to thank our sponsor, DDN, for helping to make LUG and in particular this tutorial session possible. And now I would like to introduce our last speaker, Nathan Rutman. Nathan Rutman started working on Lustre in the early days at Cluster File Systems, designing a number of the features, including the MGS and MGC, adaptive timeouts, OST pools, change logs, NRS, and HSM. He's now a storage architect for HPE, working on other projects, but still considers himself one of the old men of Lustre. So Nathan will be talking about getting the most out of Mirror and Migrate.
All right, first of all, can you guys hear me? Rick, I'll take
Yes. Yep.
Thanks. Okay, good. This just a bit of administration, I guess. This presentation might not be as long as we have scheduled, so we might let you guys out early for lunch, but we'll get it going here. This presentation touches a little bit on what Rick has been talking about with mirroring and PFL and SEL, and a little bit of what Glenn was talking about earlier about benchmarking. This topic kind of has a little bit of a different spin on it, so we'll just get right going. If I can figure out how to advance my slides. There we go. All right, so what is or are Mirror and Migrate? As Rick pointed out, layouts are fixed. Once you create them, for the most part, once you write data into them, they are constant. So you can't dynamically move where that data is with respect to what OSTs they're on until you actively try and do something to change that. So that means that there's kind of ultimately two ways of moving data, changing those layouts, and those basically are mirror and migrate. So as we heard, mirrors are one of the types of layouts. Layout is just simply a mapping of file extents to OST objects, as you saw with very extensive details from Rick, kind of exactly what those look like with LFS get stripe. But I'm not really talking about mirror and migrate as layouts. I'm kind of talking more about them as verbs. What does it mean to mirror and to migrate? And in that sense, what we really mean, mirror and migrate, is really about that copying and movement of data. So what are mirror and migrate not? Mirror and migrate are not namespace changes, right? So nothing moves, and this is a little bit hard sometimes for people new to Lustre to kind of really understand, is that when we say migrate a file, we do not mean modifying the namespace of the Lustre file system in any way. Right? The file doesn't move like your traditional move command would put a file in a different place in the file tree hierarchy. Additionally, the file metadata, not just its place in the tree, but the metadata itself isn't changed for the most part. So things like the file identifier and like your users and UID, GID, that kind of stuff, the C time, M time, those are not affected by mirroring and migrating. So migrating does not change, for example, the M time of a file, which you might almost expect it to do. There is a little bit of internal Lustre metadata that does change, obviously, when you do something like that, which is the information related to what the layout itself is. So that's stored in an extended attribute in Lustre called the layout EA, and so that does change. But for the most part, the metadata that you look at in a file doesn't change at all. Whoops, in the wrong direction. There we go. Okay, so as I said, what do mirror and migrate mean as verbs? They mean copy data. They're mirror and migrate both copy data, and then there's some kind of atomic operation once you've finished copying that data that tells Lustre that the layout is now modified. Right. So we for migrate, we copy the data, and then we destroy the original layout. Right. Destroy the original data. So that is what a migrate does. Is it moves data, and this is performed. I don't think Rick actually showed it in his talk, but LFS migrate changes the layout by, I mean, maybe he did touch on this, by copying the data, and he was using LFS to do so. So LFS migrate copies the data from one layout and copies it into a different layout, and then does this atomic switch of the layouts at the end, so that, like I said, the metadata doesn't change. So we keep the namespace, we keep the file identifier, all of that stays the same because of the swap. So yeah, and then the mirror does something similar, except that we don't delete the file at the end. We just add that second layout to the first layout and change, call it a second mirror component now. And we have that both layouts now referenced in the same extended attribute. All right, so why do we want to do those things? Why would we care about moving data around in the background? The first and major reason for doing so is to change the striping pattern of a file. And really, this is about optimization. So this may be something like, well, we didn't realize that this one stripe file that we created was actually going to be huge. We were just kind of ingesting data at the time, in our our log file, and didn't realize it was going to be, a half a petabyte large, and really want it to be, accessible by multiple clients simultaneously. And so it's the wrong stripe pattern, and we need to change it. We might also change it because we decided, we wrote a better application that is, more parallelized and can actually take advantage of the fact that we split up our file across multiple OSDs. Some of the, well, a lot of the work actually that went into designing features like PFL and SEL and those kind of very complicated auto elongating layouts that we just saw, that is in response to the fact that you can't change layouts. So because we can't change layouts, well, people didn't really know how big their files were going to get, or didn't want to have to figure out kind of what the optimal pattern was going to be at the beginning. And so PFL is kind of a compromise to try and figure out, well, we'll assume it's one stripe unless it grows too big, and then we'll make more stripes, and then even bigger, then even more stripes. So that helps, but it's still not optimal, right? So that gets you a kind of a one size fits all kind of layout, but it's not optimal for any one case. So there's still maybe a desire to be changing that layout once you've established your file to something that that is more appropriate to whatever application you're running. Another reason why you might want to migrate files is because you have different tiers of storage. Let's say you have a flash tier, a flash pool, and a disk pool, and you want to move the data from one to the other because, hey, you want to leave it on disk for most of the time because that's kind of in case people want access to it. You don't want to take it offline. But you don't want it on your flash because your flash is expensive and fills up. But when someone wants to run a job that is, highly performance dependent, that really wants your data to be on flash, maybe you want to migrate your data to flash, before your job, and maybe you want to migrate off your flash after the job. So that might be a good reason to migrate. Similarly, you might want to use a mirror in a kind of a similar situations. Well, I want to have my data mirrored on both disk and flash so that it's kind of I have a slow disk backup of it, but it's on flash for my primary use case when I'm actually doing I/O to it. Another reason you might want to migrate data is if your data is on an OST that's more full and you have some OSTs that are less full. Maybe you added some new OSTs to your file system and they're empty, but yet Lustre doesn't really treat those as empty necessarily and doesn't try to necessarily favor those OSTs, or it maybe doesn't favor them as much as you need them to, or you want to just more kind of more instantaneously have a more evenly balanced file system. Then you might want to rebalance some of your files that are on the fuller OSTs to the emptier OSTs. So you might want to migrate those. And then finally, kind of a subset of that, you might want to drain an OST if you're some old hardware that you want to kind of take offline. You need to move all the data off of that old OST and put it on your new continuing OSTs. And then maybe a final point is that really the striping doesn't matter if you're talking about small files. Small files effectively will be, well, you can just imagine that the way Lustre works, if anything less than a megabyte, it's pretty much going to be a single stripe anyhow. And so none of this really matters until you start to get to large files. So even things like flash pools and disk pools. Well, if you're talking about small files, you might just want to leave those small files in flash. If you've done any kind of analysis of the amount of storage in your file system, most of the time you will see that if you add up all of the small files, they add up to a very small percentage of your total space consumption. So for many cases, you can just leave the small files on your flash OSTs, and you don't really even need to bother to migrate them. So anyhow, so like I said, most of the time when we're talking about moving and when we care about striping, we really care about striping for large files. All right, we just saw a little bit of this again from Rick. This is how you kind of create a mirror with LFS today, and how you do the data movement for those two things. So when your verbs now, LFS mirror resync and LFS migrate do the actual I/O. There's also a bunch of LFS commands that we just saw, many of them from Rick, but I'll check out the man pages if you want to kind of remember how to do all that. So, like I said, we want to move large files, right? That's the most useful output we can get out of doing these mirrors migrates is most bang for the buck we can get is when we're operating on large files. But the LFS commands, migrate and mirror, only operate on a single client, and they're single threaded. So we have a little bit of a mismatch. We're talking about large files, and we're talking about single threaded on a single Lustre client. So there's, we can start to see like why this is maybe not an ideal situation. To point out that because these are copy operations, right? This data movement is a copy from one OST to another OST via the client. The copy operation is actually both an I and an O, right? It's a read and a write. So that means that migrating a gigabyte of data costs us 2 gigabytes of data transfer, right? So it's actually going to 2 gigabytes through your NIC on that client. And also another point about that is that I/O is serialized. So you first have to read and then write. You can't do those two things simultaneously. So what do we want to get performance? We obviously need to parallelize, right? We have on a parallel file system. Why shouldn't we be parallelizing all of this data transfer? Of course, the answer is because it's complicated. So that's what the rest of this presentation will kind of be about. So what do we want to parallelize? We want to parallelize both across a kind of a number of dimensions here. We want to parallelize across the chunks of a file. So take a very large file. We want to parallelize moving those extents of those files in parallel so that we can make single file transfers go a lot faster. We also want to parallelize across nodes so that we escape our 1 gigabyte, our 1 client limit, so that we can use multiple clients at the same time to do our I/O across that are presumably talking to multiple OSTs. So we want to be able to use as many clients as we can in order to do those transfers. And then we also want to not just do one file transferred across lots of clients and lots of OSTs and lots of threads. We also want to do lots of files simultaneously in order to kind of get around that serialization problem, right? So rather than just spending our time reading and then spending our time writing, we can be reading and writing different files at the same time. All right. So as I said, this isn't what LFS does, right? LFS just is a single thread, a single threaded read, a single threaded write. I'm not even sure it uses direct I/O or not. Anyhow, the bottom line is it's quite slow. And so we need to use Luster's, we can't use LFS. So we have to use basically the same calls that LFS does to set up those layouts and to set up the source and target files. They are actually files, and then do those merges of the layouts at the end. And we need to do that across by using Luster's API directly, so LLAPI. It's relatively straightforward to do this. We just need to make sure of one thing, which is to make sure that the data doesn't change between the time we've copied the data at the beginning and by the time we finish our copy. So we get the file data version. We copy the file somehow now to a temporary file. The temporary file has your target layout that you want ultimately your file to look like. And you use your favorite parallel file copy tool to do that data transfer in parallel. By the time you finish with that, you then verify that data version and do that layout swap in the case of the migrate. So we swap the inode information, so the metadata information, the FID is now associated with that second layout instead of that first layout. And that basically is transparent to users. So the file doesn't change. It doesn't, open file handles can stay open, in fact. And all that happens is that Luster says, if you asked for the information in that file, what used to be, I used to be able to tell you that information was in layout version 1, and the OSTs that reference particular extents are this and that. Now the layout information is layout version 2, and the OSTs are elsewhere. And so that's a pretty easy thing for Luster to do, and ever since the migrate command was kind of first introduced, has worked actually quite well. And then, of course, to get more of your parallelism, you run this on lots of files simultaneously, and you have to have some way of kind of coordinating this across multiple nodes, some kind of distributed job then to keep track of which files you're doing and if those files are doing different chunks, etc. So mirror is not quite so easy. because there's a problem with mirror which really is a result of there being a single the implementation in LFS was single threaded and single node. No one ever bothered to try this, to try running a parallelized version of mirroring. And so there turns out there's a problem with it, which is that there's a least lock that's required to resync the mirror, and that can only be held by a single client. And so that means you can't actually start writing from more than one client at a time. And there's actually a ticket, and this is actually fixed, I think, in 2.15. So so this is no longer quite such a problem. But the workaround is also quite easy as far as that goes, which is instead of calling it a mirror, you just call it a migrate. Break the mirror into two files, right? So your original file and your and the file you want to resync. You create a you can basically delete the data out of the second file, or simply create a new one. You can just create a new temporary file with your desired layout. You copy the data just like you did in Migrate to the new temporary file. And then at the end, once you've finished and verified that that hasn't changed, the layout version, the data version hasn't changed, then you just add that new temporary file back to the first original file as a new mirror. So you take out the old mirror, create a second file, add it back as a new mirror. And that works quite well. And then you don't have to worry about this other issues about layout, about least locks. I don't see any real problem with doing it. It's maybe a little more operation, sorry, excuse me, than maybe a slightly more ioctal operations than just doing a mirror by itself, but it's really not much. And like I said, we're talking about big files here, so the overhead of a few extra RPCs isn't really that big a deal. The metadata RPCs when we're talking about really large IO operations. All right. So another kind of question as well, if you're going to do this and you're not going to use LFS, how do you specify what that target layout should look like? We really don't want to understand all of those same flags that LFS uses, right? You saw how complicated some of those commands could get. LFS is changing all the time as new features are being added to Lustre. We don't necessarily want to have to follow all of those changes when we're writing kind of our parallelized version of a copy tool. And so instead, we can kind of use the same thing that LFS does with its idea of a victim file, which is that we just use an example. So we have a template, a file that has a layout that's defined already somehow by you setting your LFS command in the first place. So you use LFS set stripe, whatever you want, however fancy, complicated PFL, et cetera, SEL layout you want. And then you just pass that file kind of as a template and say, use that file as an example layout for the file that you are going to create as a victim file or as a temporary file, basically. There's one other kind of slightly annoying complication, which is that if that template file that you are creating now is just a simple plain layout file, actually then Lustre refuses to add a plain layout file to a composite layout. So that means that you can't add a plain layout mirror to a composite file with my little methodology I introduced above. So instead, there's again, a very simple workaround, which is kind of force the plane layout to a composite layout. And you can kind of do that with a couple of API calls, of LL API calls, which is basically, you just get the extent as a component. So if you say layout component extent get, that actually turns on the composite flag, and then you just set that extent. Actually, I guess it's the component extent set that actually sets that flag, and then it suddenly is now a composite layout, and you can add it to your mirror, and all is well. So these are just things that we kind of had to work through as we were implementing this parallelized tool. Anyhow, all right. Now, as I said, we're trying to get the most out of this. We care about performance. And so how do we actually measure performance? Glenn told us don't use DD. So I'm using DD. Actually, I'm not really doing that. What I'm doing is using DD to create a bunch of files, and that's actually a really convenient usage of DD. So in this case, I am creating files. I'm creating 99 files in what am I doing? I'm actually copying it. Looks like 99 files. Oh yeah, I am doing a little bit of performance. Okay, so I'm copying 99 files at a time with a block size of 64 megabytes using direct IO, and doing that in parallel on a single client. So it's not the same thing as using IOR, of course, but for a quick, simple test and kind of comparative values, it's quite easy to do this. And like I said, what we're doing, or maybe not like I said, but what we're doing is actually doing at this point a optimization of the performance on a single client, and then we're going to kind of worry about scaling it out to multiple clients, kind of in the next phase. There's a little trick actually when we're talking about lots of large files. There's a trick to create lots of large files quickly, which is just to use truncate. So with Lustre, when you truncate a file to a certain size, it actually doesn't fill that file with actual data. But because what we're doing with our test is actually mirroring and migrating that data, so we're actually copying that data anyhow. So the fact of copying it means that despite the fact that it's full of zeros by virtue of me creating it with truncate, when I read it, it still looks like a bunch of zeros. So I can still get a good measure of the copy time, or at least the write time, by reading a bunch of truncated files. And then once I've migrated them, and I'm in my measurements, I'm migrating them back and forth and back and forth. So at this point, because I'm migrating back and forth, they've turned from a bunch of zeros to a bunch of fake kind of zeros with in the sparse file implementation of just the truncate in the first place to actual zeros. And so despite the fact that truncate doesn't actually fill it with anything, by the time I've done migrate a couple of times, they actually are all full of zeros now. So they're actual data. So the next so this is basically a little list of kind of little tricks that I was using to get kind of some performance measurement information, and it turns out to be a little bit hard-earned tricks that might serve you well in the future for your own performance measurements if you're so inclined. Okay, so the next thing is we cared about direct IO. It made a big difference in our performance measurements, and so I wanted to see like how many files we were actually getting doing direct IO at the same time. And that's not really an obvious thing to get out of, because that's Lustre kernel stuff. How do you know where it's going in the kernel? Well, it turns out that if you look at the kernel, you can find out. You can look at the kernel stack in Linux, and you can basically count the number of times that you see the LL direct system call, or it's not a system call, it's a member of the stack trace there. But it's that is what's invoked when you're actually using direct IO. So you can this little command there counts up the number of stacks that are waiting, the number of processes that are well, in this case, actually tasks within a process. So counting up the number that are waiting in direct IO. So that was a kind of a useful thing. So I actually know like how many tasks there are total. And so if I have like 64 tasks and 27 of them are in direct IO, that was, well, that's a useful bit of information to me to kind of figure out where I can get some optimization out of this. Also, it's kind of useful to see the number of open file descriptors. For our particular application, we wanted to get to do a lot of parallel operations with lots of files. So we wanted to see how many open file descriptors we have. So that's both the read side and the write side. And so you can kind of do that again with a proc file in Linux. And then there are some useful Lustre stats as well that you can look at. You have to turn these on, the extent stats basically, and the RPC stats by initializing them with a 1 or a 0 basically to clear them and start them. And once you do that, then you can you can look at the sizes of your system calls. So the extent stats will show you the size of your system calls. So like how large are your reads and writes? In this case, this looks like 100% of reads and writes are at 8 to 16K, and which are may or may not be important. The RPC stats are the size of the actual Lustre RPCs. So Lustre will combine the extent stats, like system call stats, into fewer RPCs as it can. So that's actually what you care about. So in this case, these are all 100% 1 megabyte RPCs in this case. Or sorry, no, those are 4 megabyte RPCs. So 1024 times the 4K block size. So that's actually good. So 4K, so 4 megabyte RPCs are pretty optimal as far as Lustre is concerned. So that's so this is actually a good result, not a bad result, despite the fact that our extent stats are small. And then again, since I was using kind of a single client to do my my IO performance optimization at this point, I was using a tool called FIO, which is not an MPI tool. It's quite easy to use, and you can kind of write up scripts that control very closely a lot of different options in terms of IO paths and simultaneity of kind of read and write operations. You can kind of see some of the options here, and there's it's nice and repeatable because you can define basically all of your options in a job file, and so it's easy to kind of just, when you type FIO and you just point to the job file and it does all this stuff, and so you can kind of have different profiles and try out different things and just keep track of what you've been doing over time to kind of get an optimal set of parameters. Okay, and then to measure the performance, how do you see what? So FIO will give you an overall throughput number, just like IOR will, but that is really not sufficient when you're trying to really understand what's going on with your performance. They give you overall averages, right? They give you, as Glenn went into the extensive detail, they give you with the deadline kind of based stonewalling, the stonewall endpoint of the run in order to avoid long tail effects. Well, you don't really know what those long tail effects are. You just kind of hope that you can avoid them by messing around and playing around with those numbers frequently enough. But there's really no substitute for actually seeing, well, where's the actual data slowing down? Where are we, who is the long tail? How long is the long tail? And so I feel very strongly that those kind of tools like MPI and FIO, while perfectly fine for measuring overall average throughputs, they don't give you the level of detail that you need to kind of really understand what's happening kind of in the quest for an optimization. In this case of code, if you're not able to change the code and you're just trying to change parameters of your performance measurement, that's a little bit of a different story. But there's a lot of information that's encoded in kind of the time-based performance throughout the run. Right. Anyhow, so this is Grafana. This is happens to be across. So we use Grafana, and this happens to be Kubernetes and Prometheus that collects data. All I'm doing in this case is collecting the performance, the data throughput of the NICs themselves, of the network interfaces. So in this case, these are InfiniBand NICs, and we are just looking at the data transfer through the NICs. And in this case, this is all I care about is just writes, I believe, because the writes and the reads are the same, because that's my workload, right? I'm reading this, all the data that I'm writing is the same data that I'm reading. So this, in this case, is showing me my total throughput and kind of what each of my different nodes is doing. I also, in this particular case, happen to be graphing the IO operations, but I don't really care because they're relatively small. In this case, and what I'm showing here, they're not small, but in my desired use case, they are. I'm also graphing, in this case, the CPU. And this red line represents kind of a maximum allowed by Kubernetes, and so I just want to make sure that I'm not hitting my limits here. So, okay, what I just told you that FIO can actually measure a lot of different, can use a lot of different IO engines. So that was part of my investigation as well. Well, what do different IO types imply for the performance that I'm getting out of my copy operation? So send file, which sounds like a good use case for this type of workload. So my workload is I am copying from one set of OSTs to a different set of OSTs, basically one file system to another file system as far as the local client is concerned. But it should be kernel to kernel, right? I don't need to see this data in user space. So send file is a Linux facility that does kernel to kernel copy, which sounds like it would be fast. And so I tried using send files in our first implementation of this tool, and found that it really actually is not fast, because what it seems to be doing, looking at those OSC extents, so that extents file I was looking at before, it was showing that we were writing really tiny chunks, and tiny chunks at a time. And so there was none of that aggregation that Lustre does much more nicely in other areas. And so it turns out that send file, while it might be nice in theory, in practice, in this case, really wasn't useful. And instead, using just direct IO was much faster and had a much lower CPU. There's a little bit of a problem with direct IO in the general use case. which is that you have to write sector aligned sizes. So if your sector is 4K size, then and your file size happens to be some non-multiple of that, then trying a DIO write of your last sector will actually fail, or your last segment will fail because it's not a multiple of 4096. So you have two options. You can either overshoot using direct IO, in other words, just record some extra data at the end, and then truncate the file back to its desired actual size, or you can stop writing direct IO with the last, with the last remainder and change to something like BIO and the last part. But either one of those is a little bit annoying, but that's what you have to do if you want to use direct IO. And it turns out that because of this, that little hassle, using buffered IO is actually better when you're doing small files. So there's a transition point at which it's easier to and faster just to use buffered IO than to use direct IO and with this little dance. And then finally, there's actually a new IO U-ring facility in Linux that's fairly recent development in Linux that uses asynchronous ring buffers. It turns out that Lustre can kind of handle this already with its AIO implementation. In this LU ticket, it turns out that well, we actually I didn't get as far as testing this out actually. All right. Moving on, thread counts. So as I said, we're trying to do this stuff in parallel. What is the best thread count that I can run on each client in order to kind of optimize my performance? So again, I'm using my FIO tool to modify and change the number of threads to see where I'm getting the best overall performance. Turns out it was 112 threads on my particular clients. And we can see, looking at kind of this segment of the IO stat, or no, these are RPCs in flight. You can see that I was getting, with this number of threads, I was getting kind of a maximum around, I don't know, 4950 RPCs in flight on the read side, and a maximum of around, somewhere around there, 53, 54 RPCs in flight on the right side. So I'm just looking at that percentage column, which is kind of in the center, and looking for kind of the peak of the hill. So RPCs in flight is a dynamic, it depends on what your actual processes are doing at any one time. And so you're never going to get a very clean number here. You're going to get kind of more of a distribution. And so in this case, I'm just looking for the top of the hill, the kind of the higher the RPC in flight, the better. So I'm kind of measuring this using this as a proxy for understanding the number of simultaneous reads and writes. So I am seeing that, as I said before, we can kind of look at the number of direct IO with my special little stack looking command, and I can see that I got 108 threads kind of doing direct IO simultaneously. It's good. So I'm basically, the reads and the writes are all doing direct IO, almost all of them. So this is a good situation here. All right. So one of the other things that we talked about earlier was that we need to break up files in order to parallelize them and run IO on them simultaneously. Well, how big a chunk should we make? How should we break those up? Should we, for example, have each node run from one OST in a multi-striped file? So you might think that, oh, well, that makes sense. Then we can kind of have a one-to-one OST to client ratio, and every client will be talking to a single OST, and they can, there's to be no interference from other OSTs. So it's true that there's no OST contention in this case, but the performance is still pretty bad, because what we've done now is we've broken up, we've kind of eliminated the idea of read ahead. So, for example, if our stripe count is 4, and we're reading, and we break up on these 1 megabyte boundaries, then from each client that we're doing this, or each thread that we're doing this, we are reading 1 megabyte and then skipping 3 megabytes. So we're kind of throwing away all this potential read ahead information and skipping around as far as the continuity of the file itself is. And so that turns out that Lustre is not really happy with that use case. And besides, because we are explicitly changing striping with this application, right? The whole point of this was to mirror and migrate generally to a different striping pattern. We don't really know that the number of OSTs on our read side is the same as the number of OSTs on our write side. And so we can't really use that information to kind of try and optimize what we're talking about anyhow. So turns out that it doesn't matter, because reading large buffers on every node is actually better anyhow. So if we just try to read, for example, 64 megabyte chunks, using as many OSTs as that takes across as many clients as we have, that just gets us the best performance. And probably people that are more familiar with benchmarking would have told you from the beginning. In fact, Glenn, I think, mentioned in his presentation, many to many is really generally the right answer to get optimal performance. I was hoping that I might be able to kind of tune it a little more closely based on my knowledge of the stripe size, but it turns out not to be the case. So, so we can see in my graph here, I kind of just, my chunks, let's see, my graph is maybe not telling me anything interesting. Yeah, anyhow. Okay, so now at this point, I've got my chunk size, the right size. I've got my IO pattern, what I want with direct IO. And I've kind of distributed my job. Now I want to really kind of crank this thing up and see what I can get out of a fast Lustre system. And so we connected this to one of our faster Lustre systems. Everything you saw kind of before now was just on our kind of local test cluster. And so, so doing this, now I can see that my graph is nicely kind of even at the beginning. And I've got a multi-rail node here that is running kind of almost twice as much data as my other 3 single NIC nodes. I can see a couple of things interestingly from this graph. One is that on the bottom graph down here, I can see that I'm topping out my CPU usage, so it's hitting my throttling limit. So I know kind of immediately that, oh well, I need to increase my CPU limits in order to get more performance out of this. I also see kind of another interesting point, which is that the node with the two NICs, the multi-rail node, is finishing much more quickly than the rest of the nodes. So when we talk about a tail, right? There's a lot of tails. There's a tail after the first 5 minutes looks like this process, where we suddenly drop from 60 plus gigabytes a second to 47 gigabytes a second. And then there's another kind of slow drop down, and then we kind of hover around 20 gigabytes a second for a while. So that first, and this is kind of like I said before, why visualization is critical. It's like, well, I can see that the reason that for this first drop is because this kind of light blue color and this purple color finished their work. And those are the two, happen to be the two NICs on my dual NIC node, which means that I didn't distribute work, didn't give them enough work. They're operating a lot faster because they have two NICs, and they're basically the throughput of that one node is twice as fast. So it finishes its work, and then it doesn't do anything else for the rest of the time here. And so as the faster nodes basically finish their work, all we're left with is the tail. So what this tells me is that, well, I really need to redistribute work to those faster nodes, or give them more work in the first place, in order to optimize my overall kind of throughput time here. This also, it depends on your workload. If you're continually throwing new data at this, well, then depending on how you allocate that data, maybe you just give your less busy nodes more work, in which case you might start filling up your faster node again. All of that's kind of dependent on what your application actually does. In fact, this slide goes into the detail of what I just said. So that's my load balancing problem, is that I've finished my work, my fast node. The other three nodes kind of carry on. One of them finishes, a little sooner, or a little bit afterward, or some of them finish various threads that they're working on more quickly, and then they're left with the slower threads, or the slower files that they happen to work on kind of until they all finally finish. All right. So what are some of the things that I care about, or some of the kind of gotchas along the way? So RPCs in flight is an important one to make sure. As you saw, I was getting my optimal performance with 112 threads and 64 RPCs in flight. Or 50, whatever it was, 53 RPCs in flight. That is much higher than the normal RPCs in flight that is kind of the Lustre default, which I believe is still 8. So I make sure that you kind of tune up those parameters when you're doing your own. Again, these are single client reloads, so I am trying to kind of optimize for single client. So. Lustre version 2.15 has a lot of fixes for a lot of things, including those mirror creation issue, as well as there's a lot of single threaded file performance improvements there that in my case don't make a difference because I'm using lots of threads, but depending on your application, you may very well appreciate that. Pay attention to CPU throttling or CPU limits. If you have some kind of environment like Kubernetes that does impose CPU limits on different processes. And then you can also see, again, kind of one of these things from an issue that we had that took a very long time to figure out is evidenced in this graph. Where we are looking at some relatively decent performance at the beginning. Don't pay no attention to the absolute values of the numbers here, but the relative performance, where we have three nodes in this case. Two of them are very quick, and one of them is very slow. The little pink guy on the top graph is very slow the whole time. And it takes a long time to finish, and so that means the overall throughput of the whole system is very slow, because if you're waiting, timing just the beginning and end. So what's going on? Is there bad hardware on this one node? Is it the IB firmware version? Is this node doing something else and is busy doing something else? Also, you can kind of see the CPU on that one node kind of goes a little nuts. Turns out none of that was true. The actual case was there was no hardware issue. This was also this happened to kind of float around. It didn't seem to be there consistently, and it actually seemed to change nodes. So this was we thought, well, maybe it's something going on with Kubernetes. No, none of that. It actually turns out that the whole problem was that we had Lustre debug turned on that one node. And so turning off Lustre debug solved the whole problem. That's it. Wow. Took longer than I thought. Sorry. Yeah. So anyhow, the overall point of this was kind of show not just what kind of mirroring and migrate are, but maybe also a little bit of investigation into performance issues and what's going on, and kind of a little bit of tools to kind of see as you're doing your own performance investigation and your own performance tuning, some things you might try out and kind of take a look at, and things that might be important, and tools that you might be able to use to kind of help you get the most out of your Lustre system as well. That's it. Thank you. I'll be happy to look at any questions. Andreas points out that LFS mirror will preserve holes, interestingly. So my little truncate trick won't work with LFS, although depending on if your own application may or may not care about or preserve holes, then potentially you can still use the trick. But it also points out the fact that, well, if I want more performance out of my system, that I should also pay attention to holes and make sure that I do the same thing that LFS is doing in this case. And then Cameron Har asks, I'm currently trying to migrate millions of files to other MDTs and it's slow. So if you're if you're actually talking about migrating files between MDTs, if you're talking about kind of so there's a little disconnect, right? So what I'm talking about is layout changes, which are really OSTs, and the MDT layouts can't be changed easily. So you can't change a DOM layout to a non-DOM layout with these tools, as far as I'm aware. And I might be wrong about that, but I'm fairly certain you can't actually change. You can't basically move a file from one MDT to another. So maybe that's part of the question, or maybe you misstated and you meant OSTs. But in any case, and there's another, I guess, possibility, which is you can migrate the directory, so that's the namespace changes, to a different MDT, I think. But that's again not what we're talking about here. The bottom line is, if you're trying to move, if we're assuming that we're talking about kind of layout changes in general, if you're really trying to move, millions of files from MDTs back and forth, there's really no secret sauce. You have to do it in parallel with as many nodes as possible, with as many threads as possible. Like I said, using direct.io is definitely helpful, and using larger chunk sizes is helpful. If you're talking about millions of files, I don't know if those millions of files are small or large, but smaller files just take a long time, kind of on a per byte basis. Right. Okay. He explains that he is worrying about DNE2 and DOM. Yeah, I'm pretty sure that's correct, that we can't migrate DOM files. That potentially worth. I might be corrected there. I think those are the only questions I see. So I guess we'll call it the end. Thanks, Rick.
Thank you, Nathan. Well, that wraps up our tutorials session for the day. I'd like to thank everyone for attending. We had a really great turnout today. It was good to see everybody show up for these tutorials. I'd like to thank our presenters once again, Andres George, Glenn Lockwood, and Nathan Rutman for volunteering their time and sharing their expertise with us. Thanks once again to our sponsor, DDN. We'll let everybody know that the slides of these tutorials will be posted online at some point in the future. We just don't have a date yet for that. And I hope to see you all tomorrow for when the LUG talks start. Thank you.